Pleasure to be here today. Although I did start out in chemistry, I'm afraid I don't remember very much of it now. My undergraduate degree was in chemistry, but I went on in physics, and I'm in the physics department at Santa Cruz now. And much of the work I'm going to talk about today was work that was done by the Veritas collaboration as a whole, and I want to, so in that sense, much of what I'll be presenting is for the Veritas collaboration. So the Veritas telescope array is a prime example of an atmospheric Cherenkov telescope array. It's in southern Arizona at the Whipple Observatory. It consists of 4 12-meter aperture telescopes with a fast photomultiplier tube camera at the prime focus of each. So let's begin by looking at what these telescopes were designed to do. And when a gamma ray shower interacts in the atmosphere, it produces a shower of secondary particles. Those particles are relativistic and are producing Cherenkov light in the atmosphere. That light illuminates a region on the ground that has about 120 meters in radius. If you put an optical collector within that light pool and collect the light and focus it onto a fast camera, you can take an image of the shower development in the atmosphere. And that's exactly what these telescopes do. The camera at the prime focus of the telescope has 499 photomultiplier tubes. Those are read out by 500 megahertz flash ADC electronics, and we end up then with an image of this shower development in the atmosphere. The image in each camera, together with the telescope's location, determines a plane containing the shower axis. And so if you have multiple views of the same shower from different telescopes, you get intersecting planes, and you can determine the position of the origin of the gamma ray on the sky, and you can also determine where the gamma ray would have struck the ground if it hadn't interacted in the atmosphere. And the camera field of view is about 3.5 degrees. The scale of these showers is a few tenths of a degree in width and maybe an order of a degree to 2 degrees along the long axis. So we need a wide field of view, relatively coarse pixelation in order to image these showers. We reconstruct the energy of the shower from the amount of light that's produced in the shower, and we can discriminate gamma ray showers from other kinds of cosmic ray showers, such as from protons or helium nuclei, by the shape of the shower. So one of the things that's important for thinking about using these telescopes for optical SETI is how we decide which images we're going to record. And this is done by the trigger system, which has 3 levels. So at the first level, at the level 1, there's a discriminator on each of the photomultiplier tube signals. Those discriminator signals are fed to a pattern trigger, the so-called level 2 trigger, which looks for a pattern of 3 nearest neighbors that fired their level 1 signal within a 5 nanosecond time window. And then finally, the signal from each telescopes are fed to the level 3 trigger, where at least 2 of the telescopes are required to have a level 2 trigger within a 50 nanosecond window after you correct for the propagation delays between the different telescopes, depending on where on the sky the telescopes are pointing. Now, the thing that's sort of for optical SETI, we have a very high level of coincidence. So the night sky background is a very small impact for us in terms of looking for signals. The thing that's not particularly ideal for optical SETI is this level 2 trigger, where for an optical signal from a distant source would be a point-like source on the camera and wouldn't necessarily illuminate 3 pixels, except for the fact that the optics that we have are relatively coarse, and so the point spread function, in fact, is comparable to the pixel size, and so light does spill over from 1 pixel into its neighbors. So let's take a look at what some shower images look like in Veritas and think now about what an optical SETI signal would look like. An optical SETI signal would be a point-like signal at the same position in all 4 cameras, so consistent with being at infinity. This set of 4 images on the left here are the images from a gamma ray shower. They're not a gamma ray shower, a cosmic ray background shower. So these images fill a large portion of the camera, and they're different because the shower is in the atmosphere not at infinity, but relatively close to the telescopes. They're in different positions in each camera. This is a shower. This is an event that looks a little bit more point-like in each of the telescopes, but it's at a different position in each camera, again indicating it's at relatively low altitude. If we keep looking, we can find images that are point-like and that have the same position in both cameras. This is from an analysis we did looking for signals from the Kepler star 846-2852. And we did find a few events that were consistent with point-like sources. However, they weren't at the position of the star we were interested in, so they were background events. And it turned out that this event that you see on the left here was one of a sequence of 4 events that sort of marched across the camera. And this turns out to be consistent with a high-altitude satellite moving through the field of view. So one of the searches we've done with Veritas is the search for optical flashes from the Kepler star 846-2852, which turns out to be in the same field of view as a gamma ray AGN, which Veritas had taken data on over several years from a period between November of 2008 and October of 2015. So we're able to go back and look in this archival data to see whether we had any events consistent with an optical SETI signal from the position of the star, and we didn't find any. And we estimate our sensitivity we would be sensitive to flashes that were about 1 photon per square meter. This plot shows what our spectral response is for the Veritas telescopes. So the green curve here is the overall spectral response peaking in the 400 to 450 nanometer wavelength region. At the ultraviolet end, it's primarily cut off by the atmospheric transmission, which is this blue curve. And at the red end, it's primarily determined by the quantum efficiency of the photomultiplier tubes, which falls off above 550 nanometers or so. Increasingly, new generation Cherenkov telescopes are moving from conventional bialkali photocathodes to silicon photomultipliers, and these typically have more red response. So future telescopes potentially will have better response in the red. This table from Schutz et al. 2016 summarizes some of the recent optical SETI observations, and in particular, their sensitivity in terms of photons per square meter in this last column. The searches that use 1 meter class telescopes typically obtain sensitivities that are of order 50 photons per square meter. The Stacy experiment, which used the heliostat field of the Solar Research Facility at Sandia National Laboratory, was a non-imaging atmospheric Cherenkov telescope and achieved a sensitivity of about 10 photons per square meter. And finally, Veritas, the imaging atmospheric Cherenkov telescope, is reaching a sensitivity of 1 photon per square meter. These final 2 rows in the table are observations that were specific to this Kepler star 846-2852. So what's in the future for optical SETI with Veritas? So unfortunately, Proxima b is too far to the south to be observed in Veritas. Veritas is in southern Arizona, but TRAPPIST-1 is far enough north to be observed by Veritas, and is just coming out now from behind the sun, and we have plans to start observing it for about 2 hours starting in May. We're also exploring a program to devote 30 hours of Veritas observations during the next observing season from September of 2017 to June the following year to targets from the Breakthrough Listen list, the list that's published in the Isaacson et al. Paper. In addition, we have a very large archival data set. Veritas has been operating for 10 years now. We have over 10,000 hours of data in good weather conditions. This figure here shows in galactic coordinates the coverage of the sky with Veritas. We've done a lot of observations along the galactic plane, but also all throughout the sky. Some of our deepest observations are as deep as 500 hours in some areas of the sky. It turns out that of the 1,700 breakthrough listen stars, we already have observations just by coincidence of about 200 of them. And we haven't had a chance to check it for the galaxies, but probably about 1/8 of the galaxies we also will have data for already in the archive. So we can also do an archival search of the data we already have, much like we did for the Kepler star. There are two other major atmospheric Cherenkov telescope systems in the world. One of them is the MAGIC telescopes at La Palma in the Canary Islands, and the other is the HESS array in Namibia. The MAGIC array consists of two 17-meter aperture Cherenkov telescopes. The MAGIC collaboration has done some exploratory SETI observations, but they haven't published any results yet. The HESS collaboration doesn't feel that their data acquisition and trigger system are very sensitive to optical SETI sorts of signals, and they have no plans to do optical SETI observations at this time. Looking to the future, the Cherenkov Telescope Array, or CTA, is the next major planned facility in atmospheric Cherenkov telescope gamma ray observations. And this facility will have two arrays, one in order to have all sky coverage, one in Chile and one on La Palma. Both of these arrays will have four large 23-meter telescopes at the center in order to look at lower energy gamma rays than Veritas is able to do now, and then have a number of telescopes of sort of the Veritas class, 10 to 12 meter class, 25 in the south and 15 in the north. And in the south, there would also be an array of small 4-meter class telescopes deployed over an area of greater than 3 square kilometers to really have a very large collection area at the highest energies. Construction is planned to begin this year and will probably continue through about 2023. So far, the CTA consortium has not really thought very carefully about optical SETI observations and what CTA can do, but several of us are planning to start this discussion at the next consortium meeting coming up in May. Here in the US, we've been working on a prototype telescope of the medium-sized class. It uses a novel design that has a secondary mirror which corrects for aberrations and reduces the plate scale so that we can use a finely pixelated silicon photomultiplier camera at the focal plane. The silicon photomultipliers can operate with brighter stars in the field of view, and they have more red sensitivity, which would both be advantages for optical SETI. Also, this telescope has actuators on all the mirrors so that from the triggering point of view, the mirror, if necessary, the mirrors can be slightly defocused to spread a point-like source over multiple pixels for purposes of triggering. And this is something we can test during commissioning later this year. This telescope is also at the Veritas site, so it can be used in conjunction with the Veritas telescopes in order to have a really powerful rejection by looking for the same signal in multiple telescopes. So in conclusion, the atmospheric Cherenkov telescopes offer the most sensitive by more than an order of magnitude observations of specific targets. They are relatively narrow field of view instruments, and so either the target has to be within the field of view or we have to do dedicated observations, but when we do so, we are very sensitive to faint optical flashes. It's a proven technique with Veritas, and we're charting a path forward, and I think there's terrific potential longer term for development of optical SETI with CTA. Thank you.
All right, questions on this talk? Barb, down here in the front.
This is Charles Alcock. I was talking with Paul Horowitz earlier, and he suggested that a push for red sensitivity would be a big enhancement for this program. Is that something that you've thought about?
I thought about it a little bit. It's not something that's I mean, red sensitivity is not a positive from the standpoint of the gamma ray science we're trying to do, because the night sky background is brighter in the red, and the Cherenkov radiation we're looking for is peaked in the blue. So it's a trade-off. It would be, I mean, if you were to build a dedicated optical SETI sort of instrument, you could imagine putting more red-sensitive sensors along the sort that Shelley talked about before, or even sort of conventional silicon photomultipliers have more sensitivity in the red. But but it is a trade-off if you're wanting to do gamma ray science with the same instrument.
Phil Lubin down in the front there.
As I understand your trigger, you require rather fast pulses, correct?
That's right.
And so if there was a CW source pointed at you, you wouldn't notice it, is that correct?
We probably wouldn't notice it. I mean, at some level, a brighter source will raise the rate of single photons and will raise the false coincidence rate. But if we're looking at, particularly if we're looking at stars, I mean, the stars themselves also do that. And so distinguishing a continuous, we don't have the spectral sensitivity to distinguish a narrow beam lasers type of source from the background starlight.
And if you and Shelley compare sensitivities, sort of étendue throughputs, how do you guys compare? I realize you're somewhat apples and oranges, but not completely.
Well, I'm thinking with the aperture that she has is of order a meter, so I'm thinking that her sensitivity is going to be of order, 50 photons per square meter, where we're at 1 photon per square meter. So I think that we'll be, at the cost of not covering as much sky, I think we will be more sensitive to the objects we actually look at.